Have you heard? The U.S. just launched a national initiative, giving AI access to government research data and supercomputing power. The goal? To help scientists find formulas and come up with brand new scientific hypotheses. The Genesis mission is a national initiative launched by the White House and the Department of Energy in November 2025. The goal is to pull together resources from America's national labs, massive research data, and private sector computing power, all to leverage large AI models and accelerate scientific discovery. Officials described it as a national scientific mobilization, emphasizing that AI is a tool, not a replacement. In a nutshell, it's humans and machines teaming up to condense years of research into a fraction of the time. Think of it this way. We dump all the experimental data and simulation results onto one massive computing platform. The AI then scans for patterns, generates hypotheses, and proposes testable equations. Finally, it hands everything over to human research teams for verification. The classic example here is AlphaFold. It's a DeepMind model capable of predicting the 3D structure of proteins, and it basically transformed the entire field of structural biology. AlphaFold's success demonstrates that AI can transform complex physical and biological problems into predictive models. This significantly accelerates drug design and biological research. A second example is the so-called AI scientist system. Here, researchers train models to automatically generate hypotheses, run simulations, and even output submission-ready paper drafts. Reports indicate that certain systems are already capable of producing well-structured paper drafts that can pass preliminary peer review. Though, of course, human teams remain in charge of experimental design and final verification. Beyond that, AI has already shown immense potential in materials discovery, catalyst screening, and detecting anomalies in massive astrophysical datasets. These cases illustrate one key point. AI is not merely a tool for writing code or generating text. It can process massive amounts of data and uncover patterns that humans might overlook. But keep this in mind. AI findings still need to be tested. AI often just gives us high probability guesses. So, it's still up to human scientists to verify the results in the lab. In summary, AI is shifting from a mere tool to a collaborator role. But the division of labor remains clear. AI provides the candidates, while scientists are responsible for verification and ethical judgment. In the next chapter, we'll take a deep dive into the technical roadmap and inner workings of the Genesis mission. The technical roadmap of the Genesis mission is built on three core pillars: data aggregation, supercomputing power, and an interdisciplinary public-private partnership platform. First is data aggregation, consolidating data from national labs, universities, the private sector, and historical experiments into a single machine-readable data lake. This ensures the AI has a sufficient sample size to learn from. Second is supercomputing power. National labs and private cloud services provide massive GPU and TPU clusters to train and fine-tune these large-scale scientific models. Third is the interdisciplinary platform. It brings together AI engineers, domain scientists, data engineers, and ethics experts onto a single collaboration hub. This creates a closed loop: AI output, human evaluation, and experimental validation. When it comes to implementation, the mission has to tackle some serious technical challenges, namely standardizing data, tagging metadata, and handling privacy and access rights across different institutions. When it comes to policy and compliance, we have to bake in security controls, access audits, and strict tiering for sensitive data. This is crucial, particularly in high-stakes fields like biology and nuclear power. Tech-wise, we're facing some real engineering hurdles. It's a balancing act. How do you apply differential privacy and encryption while keeping the data actually useful? And how do you securely run federated training across different service providers? In a nutshell, this mission layers complex engineering, policy, and ethics on top of each other. Now, let's look at how this hits the ground in fields like energy, quantum, and life sciences. From a technical standpoint, what we call AI formula discovery basically boils down to three approaches: symbolic regression, surrogate models, and transforming black box neural networks into math that humans can actually read. Symbolic regression is the most intuitive approach. It hunts directly through the space of mathematical expressions, trying to fit data into elegant algebraic formulas or differential equations. Surrogate models are the go-to for expensive physical simulations. Basically, you train a quick, approximate model first and run your search and optimization on that instead of the real thing. This cuts down drastically on the cost of experiments and simulations. There's also a crucial technique that turns the neural network's black box output into math that humans can actually understand. To do this, we often leverage symbolic regression, XAI, and post-processing algorithms. Here's a simple demonstration of the process. Starting with some data points, the AI uses a neural network to rapidly fit the data, then uses symbolic methods to distill that into a human-readable equation. To wrap up the demo, the AI yields an interpretable equation. For example, y equals 0.98x squared. Researchers then proceed to validate the physical meaning of this relationship through actual experiments. But here's the catch. Just because it fits doesn't mean it's real. The AI might find a formula that looks statistically perfect, but it could make zero physical sense or break down the moment you try to extrapolate. In short, AI helps us narrow down the search space and propose testable equations. But true scientific discovery? That still requires human verification and interpretation.